right, let's get going. So we've arrived to the last day, Comp 15. I hope you guys have not been stressed out too much about the homework assignment. Listen to you. Listen to you. So I can make some comments on the homework assignment. I'd be happy to answer any other questions about it. Hopefully you saw my post on Piazza. It is understandable that some people will not finish this to the point of being able to both store the lyrics and search for them and so forth, because, well, programming is hard, and it was a hard assignment, and I understand that. If you haven't gotten to the point where you're finishing up, that's okay. We'll try to grade this as best we can, as far as the working on what you have done. And what that means is if you don't get to the point where you're actually going to have a compiling, working assignment, then you better make sure your README file says what you're planning on doing and says how you were planning on doing it and why, where you are in the whole situation. Oh, look, I'm seg faulting here. I don't know why, but had I gotten past this is what my next step would have been, blah, blah, blah. So from that standpoint, don't overly stress about it. You all have other things to think about, and this is due tomorrow night, and then you'll be done with it, and we will move on. It is only one assignment out of 5 assignments plus labs plus the mid-year and the final. So that's we'll leave it. I'll leave it at that from that standpoint. But please don't stress too much about it. I know you guys have been working hard. Trust me. There were like 1 million people in Halligan this weekend, and I know you're working hard, and so I appreciate that. And either way, in the end, I'm sure you'll do fine. OK, so here's what we're going to do today. I'm going to do a quick thing on showing you how to set up your main function for homework 5 so that it will accept a command line argument. I didn't realize that was the way Bruce wanted to have the input to provide. It makes it a little easier for us to test various databases. So what we'll do is I'll show you how to do that. It's not too tricky. Are there any lingering questions right now about homework 5, Jason?
Is there going to be an auto grader?
Well, is there going to be an auto grader? To some extent, yes. To some extent, it's going to be too hard because I gave you some parameters that aren't going to quite fit. For instance, the ties. How are we going to? The auto grader is not really going to be able to figure out ties very well. I mean, it probably could, but I think what it really is going to come down to is, does it seg fault? Like, that's the first thing the auto grader can check, right? I mean, look, it tries those things, and like if it actually produces output, that's like a win. But also, it can check, it can basically set it up so that whoever grades it can go through and do a lot of checks on their own to see if it's, and just do a kind of a once-over to see if it's right. I mean, we'll have some that should be the same. Right? But if it's close, I mean, close is probably going to cut it for a lot of these ones. Okay? So to answer your question, yes and no. I mean, yes, it's going to be auto grader, but it's not going to be as much because it's going to be harder to do that way. Sarah, you had a question?
Yeah, on the assignment sheet, it talked about having 2 versions of the program, one from
Oh yeah. Yeah. So Bruce actually wrote this whole web interface for it, but then he didn't publish it. And I'm not exactly sure why. He said this morning, he said, yeah, I never ended up doing it. I don't exactly know why. I will try to find out what the story is with that. And hopefully we'll get it online. According to him, it's really cool. Like, it looks neat. It's like Google. You type in the search, and then it gives you your results, right? Which is kind of fun. But I'm not sure why he didn't end up putting that online. So for now, the command line version is it. Yeah, sorry. Susie.
Is there going to be a diff test on provide?
Is there going to be a diff test? Kind of. There is a little diff test, but it really checks. I'll show you kind of what it does. But it only checks a small database file and does a little bit. So you won't be able to use that to say, oh, my stuff's not really working. I mean, you kind of will, but not really. It's not robust at all.
Is it possible it'll say it won't pass the test because of ties?
Not ties. We won't check any that are going to be ties. Yeah. Good question. Yeah, Dylan?
As far as outputs go, you seem to be following a standard procedure on yours where you put the title of the song, then the artist, and
then the lyrics, yes.
If you don't follow that specifically, so let's say you had the song title, the artist, and then you put all the context instead of reprinting.
Right, you'll get points off.
You'll get points off?
Yeah.
Okay. So
I mean, stick to the output. And part of the reason is just because let's say you had a web interface reading it, it would know, hey, this is still part of this title and song, and I mean, I guess. I mean, if it shouldn't be very hard to put those other 2 lines in there. I mean, really, that shouldn't be hard to do. Stick to what it is, yeah. Yeah, good. Yes?
How important
Naomi.
is it, like, for grades to deal with, like, memory leaks and stuff?
How important is it, good question. How important is it to deal with memory leaks? Well, this is a particularly hard problem depending on how you did this. If you don't have a structure where all of your songs live, you have to keep track of how many times things are pointing at them before you can destroy them, and then they might kind of disappear and you won't be able to get them back. I would say you will lose no more than 1 or 2 points if you have memory leaks. I mean, that would be like tops. So I would not stress about that one. If everything's working perfectly and you want to go look at the memory leaks, run it through Valgrind and see if it plops out answer, or can figure out what's gone. But don't make that a stressor. And that's it. Yeah, Phoebe. You have a loop, yes.
And then the sentinel is break with a...
The sentinels break with the little angle brackets, yep.
And the break inside is capitals.
In capitals, yep.
Okay.
Yep, I'll show you an example in a sec. I mean, it's exactly like what I've been doing most of the time before everything. Let's see, Yuval, you had a question?
Yeah. Are you allowed to print out like a prompt, like enter a word after?
Don't print any prompts.
Okay.
No prompts.
Okay.
I mean, that'll just screw up whatever auto grading we end up trying to do, because it'll go, oh, this must be output, and then it just won't know. No prompts, yeah, good. Yeah, Nathan?
Code that you have in that shows what song, or when it's like loaded each 10,000 songs, does that need to be left in?
Yeah, that should probably come out. Yeah, so
Lyrics is like 33 lines.
you can take that out. Yep, you can take that out. Now I won't give you points off if read lyrics is over 40 lines. Don't worry about that. Or 30 lines. But
You want the show progress to print out?
no, don't have the show progress to put out. I'll show you right now. So when you do this, right? So let's look at main. This is actually probably not big enough. There we go. When you look at main, okay, so oops, not main. That's not what I'm talking about. The read lyrics one is. Hang on. Let's see. Vim word. Nope. There it is. Okay. Read lyrics. Okay. So, no, that's not what I wanted either, is it? It's in the read lyric. It wasn't main. Sorry. I'm losing it. Hold on. Yeah, here we go. See how in word list here, it says false over here? If you leave that as true, it will print out all those 10,000, like every 10,000 words, it'll print out what song it's on. Just make that false before you submit it, and then it won't do it anymore. Does that make sense? Take a look at your code, and you'll see it when it does that. I mean, if it doesn't, well, I mean, we'll deal with it if it doesn't, but it'll look like output instead of otherwise. Back, yes.
Yeah. What if we like structured our main so that's where we take in the search value?
That's fine too. Like if you structured it so that you take in the search value, that's perfectly fine. Just make sure that it doesn't. Just make sure that it meets the specifications. And I'll show you an example, so you'll see if it meets that. But otherwise, that's fine. Who had a question over here? Yeah, Lydia.
Is there a place where we can look up, like, maybe not the code, I don't know if there even is code, but like, just generally, like, what the standard functions that belong to, like, the standard templates do? Like, so, like, where we can find out, like, what pushback does.
Yes. If you go to the interweb and you search for like vector C++ or CPP, right? The first thing that comes up is like, one of the first things that comes up is this.
Right.
This tells you everything that, right? And if you want to know what pushback does, then you click on pushback, and it tells you exactly what it does. Now, it's not the easiest to understand necessarily, but it does tell you about what happens. Is that what you were looking for, or are you looking for something else?
No, I mean, like, what I mean is, like, I looked at that whole page and it sort of didn't tell me.
What specifically were you looking for?
Just, I mean, like, I don't know.
I don't know. It does give an example, which is nice.
It was like my program just kept breaking every time I
Oh.
would try and call pushback, and I like could not figure out why, and it
Oh.
was something happening within that function,
And you had no idea why, yeah.
So-
Yeah, it is. It does. There's a bit of a learning curve to get the standard library stuff to work. A lot of times it's an iterator you need instead of a integer or something like that. If you want, we can chat about it offline if you want. Let's see. Vince.
What if your function is taking extremely long?
What if your function is taking an extremely long time? So we will probably have a cutoff of about 10 minutes for the full database, but we're certainly not going to only test it on the full database. So if you can get through, if you can get through 50 songs in a few minutes, it'll probably be okay. Yeah, but I mean, I'd rather you do the whole song in legitimate time. But some people just haven't designed an algorithm that works well enough to get through that whole database. That's just the way it goes. Yeah. All right. Yep. Gigi.
I can sort of read lyrics and it's only 30 lines, is that okay?
Yeah. If read lyrics is over 30 lines, that's okay, because I think it already is, I believe. Yeah. It's close anyway. Yeah. Don't stress about that one. Other questions? Okay, let me show you what this looks like on there. This is kind of hard to read. So, let's see if I can get this bigger. There we go. Okay, so in your main function here, oops, still not, hang on. All right, in your main function here, these two parameters talk about the command line arguments. In other words, you type /song search, and then you can type other flags and things after it in command line stuff. This says, this is just an integer of how many command line arguments there are. The program name counts as 1. So there will always be at least 1 here if you type nothing else after it. That's the program name. And if you want the program name, it's actually the first string in this character string of or this character array of strings, this array of character strings. There we go. All right. And what it says is, look, this is how many of these there are, and this is which ones there are, which ones they are. Here's how you actually use them. Oh, it's right here. Wordlist.readLyrics and then argv1. That is a character string of the first argument after the name of the program. Right? And so that gives you the actual thing. This says, look, if there's only 2, then we're good. If there's more than 2 and you type more stuff on the command line, well, ignore it. Well, not just ignore it, just like don't go through and do this. That's kind of the way I've done it. You can do it differently. You don't have to do it exactly like this. Let me show you how this actually works on here. All right, if I type, let's see, clear. If I type .song search and then there happens to be a poems .txt file, which is one of the things we're going to test on for the, at least for the provide, right? What it should do is, not that because I didn't go to the right, you should test this on the homework server. There we go. There we go. Song search poems.txt. Okay, it should do nothing, right? Because it's waiting for your input, right? One of the things one of the lyrics in here, or in the poem, is pebble, P-E-B-B-L-E, right? And this is what it should do. It should print title, then the artist, then the context. I think I goofed here. I think 1, 2, 3, 4, 5, 6 for some reason. I don't know. I goofed on that one. I hope that's not true for the ones I posted online. Maybe they are. I don't know. But anyway, and then it should have like a blank line here because it's after the content, and then end of report. Okay? And how do you exit out of here? You type angle bracket, B-R-E-A-K, angle bracket, and then it ends. Right? That's it. Question, Nathan?
I think that there's a song that actually has that break statement exactly as it is.
That's OK. We won't search for it.
Okay. Wait, it shouldn't have this.
I don't think it matters anyway, because you can search for break, right? You can search for break, and then it'll tell you if there's like breaks in there, right? But when you search for angle bracket break, that says stop the input, right? If you search for, now I'm not going to stress that we're not going to search for this, but if you search for like break like that, it should find all those other breaks, right? Because it strips out the thing. If you didn't do it that way, that's fine.
I had to change like the setup of the search list just because for some reason, even though it was while the search word is equal to or isn't equal to that break statement, it was still finding that break.
Oh.
So I don't know, but
That shouldn't be the case. It should break immediately. Don't let it break after you've looked for the word break. In other words, just if you see the break, then it should just End. You see the angle bracket break, yeah. Question?
What should happen if you type in a word that's not in the database?
Let's see. Unknown word. Nothing. It should say end of report. Right? It should still wait for more input, yeah. Yep. Yep. Let's see, wait. Wait in here? Yes, there's some weights in here. Did I goof on this one too? 1, 2, 3, 4, 5. I don't know why that first one had an extra. That's weird. Anyway. OK. Other questions on main? Yeah.
What is the else statement? Like, use their songs with database line that's on the outside.
Right here. This right here. Oh, so what I did was here is, OK, so I did this for 2 reasons. First reason is if you don't use argc, it gives you a warning and says you didn't use argc, which is silly. But I just said, fine, I'm just going to accept it like this. And I just put, if you type song search without anything, it would say, oh, there's not 2 arguments, so I don't have one. I'm going to go here and say, hey, this is how you're supposed to use it, dummy. Right? Like, hopefully I'll do this here. Hopefully it'll work here. Break. Song search. Yeah, see, it said, I should have said usage, dummy. Song search database txt, right? So, whatever. What's that? Is that? Oh, yeah, that's what it means, right. Right. OK, cool. Does that make sense? OK. All right, anything else? Yeah, Gigi.
In one of the mini example main files you put up, there's a live assignment.
There's a which?
In one of the example main files you put up a while ago, there's a line inside which I think a file name gets something, so we could just run some search for that.
Oh, yeah, you can take that line right out. It'll probably give you a warning saying, hey, that line doesn't ever get used. But that, yeah, take it right out.
That's what I'm using right now to test.
Yeah, no, that's fine. That's fine. Yeah. But this is the way I'd like you to do it, just because that's the way Bruce set up the provide. So that's fine. Question, Yuval?
Did we get warnings from either the alpha only function or the hash function? Should we worry about them?
So the hash function, there's 3 warnings or 2 warnings about K8 something or other. I don't know if that's the one. You can take those specific lines out.
I got more after that about assignedness from different things about it.
Don't take out all the K8s, just the ones it points to. Ones that say unused variable, you can just take those ones out in that exact line that it says. Don't take them all out, though. But you shouldn't get other warnings. I don't think you should get other warnings. I'm not sure if it's because some other flag is called in the compiler or because something changed or you're calling it with something that shouldn't be. I'm not sure. If you want, stop by and we'll take a look. But warnings are you should strive always to have your code compile without any warnings. Because the compiler is telling you something is up here that you probably need to know about. So, try to do that. If it doesn't compile, if it still compiles with warnings, well, so be it. If it still runs, then that's probably a good thing. Yeah,
I was
Charles.
going to say on the hash function, it returns an unsigned. So like that's, you should probably save that as.
No,
Alright.
yeah, but it's not. It's like it's giving me errors within the hash functions.
Yeah. I'd like to see that because I'm curious what it's doing.
That is what you
Yeah. OK. Other things? All right. If you do have other questions, let me know. I plan on being around all day tomorrow, in and out of the lab, my office. I do have to do some online or some in-person grading. Oh, speaking of in-person grading, has that been going all right? I think I've had some concerns about it, but we've addressed those on an individual basis. Otherwise, I hope it went all right. I've enjoyed like talking to you guys about this stuff because you guys really know what you're talking about for the most part. So that's good. And your sorts were very cool. Most of you guys did great on the sorts. And for those that like segfault or something, we figured out the problems and got around it. So that's the way it goes. But I enjoyed doing it. I know it took some more time than you probably really wanted to spend at this point in the year. Not to mention this assignment taking too much time. But hopefully it was all right. Any comments on it? No? OK. All right. So let's go on to just a quick review about the stuff that you could see on the final. Final exam, I believe, I just found out today that it's going to be in here. I guess they could be other places, but as far as I know, they've scheduled it in here. If I find out anything else, I will let you guys know. But it should be in here. You can go to either day. Feel free to go to either next Monday or next Wednesday, I guess it is. Monday or Wednesday. OK. And this is what's going to be on it, this sort of stuff. Most of the stuff on it, post mid-year. When I say most, I mean, look, some of the stuff is building on other stuff. So You know, it's going to be, there's going to be some things you need to know, but I won't specifically ask you, say, about a stack or about a queue, because you've already done that, right? I'm not going to stress about that. I'm going to ask you about the newer stuff that we've talked about. I believe the exam's a 2-hour exam. Yeah, if it takes 2 hours, it does. I won't make it much. I won't make it any longer than the mid-year. I want them to be about comparable. As I said before, if you do well on the final and didn't do well on the mid-year, I'll take that into consideration when it comes to your grade. Okay. And I guess the converse of that, I don't know if that's necessarily true. If you bomb the final and did great in the mid-year, you'll probably do okay, but don't go into it thinking you can bomb the final. All right. Okay, so here's the first thing that we talked about after the mid-year, heaps, right? We talked about heaps mainly because they are a data structure that is very good to use for a priority queue because of the way that priority queues are, right? You need the minimum element or remove minimum, and you only need access to one element, and it happens to be the assorted element, in particular the minimum or maximum, depending on what kind of heap you have, and it beats out most of the other types of priority queues that we have, depending on your use case. If your use case is something where you can take as much time as you want to insert, and then you want really fast searches, actually an ordered list is better than a heap, in the sense of, look, you can actually get the last element in constant time from an ordered list. Wow, that's nice. But if you want to insert and remove the minimum and get the minimum element off the top, well, you're better off using a heap because overall, though, it's more efficient. Okay. We can also use a heap to perform a fast heap sort, which is a pretty good way of doing sorts, okay, which we'll get to in a few minutes too. Remember, heaps are simply, the heap property is parents have a higher priority than any of their children, whatever that definition of higher is. In this case, higher means lower number. Higher priority is lower number for a min heap, right? There's no implicit orderings here, right? This is, heaps are not, like there's no difference between 10 being over here and 8 being over here as far as 5 is concerned, right? It just does not matter. Okay, no implicit orderings that way. That's part of the reason we can order it the way we do. Okay, let's see. Heaps are complete binary trees. Remember, fill from the left until you get to the last one and down and to the left, and then the empty ones are the leaves at the end. Leaves at the end. Okay, complete binary tree. What's nice about a complete binary tree is you can represent it in an array very nicely, in fact. Okay, and we can do this with heaps. Remember that heaps we put them in an array. We generally leave the 0th element empty because it makes the arithmetic slightly easier. What arithmetic? Well, it's the arithmetic to find your children and your parents, right? So one of the questions I could ask you on the final is, hey, what's the parent of element 12? Now, you could go and draw this all out and go, oh, it's 10. Or you could divide by 2, and interdivision by 2, and you could say, oh, 4 divided by 2 is this 2, so it's element 10. Boom. Okay, that's why heaps are particularly fast as well, because they're a nice array structure that's easy to do a little arithmetic to find your lineage. Right? Well, pretty straightforward stuff. Okay? All right, so what are some of the heap problems I could ask? Well, I already gave you one, but let's look at some other ones. Perform remove min on the heap here. Shall we do that? So you can remember how to do it? All right, let's see. 5, 10, 8, and 12, and 11, and 22, and 43. 40. Oops, thank you. Guess I can't look. How about 43, and then 14 and 13. 14 and 13. OK, so if I want to remove the 5, what do I do? Yeah, I take the 5 off, first of all, right? And I say, well, that's going to go possibly be returned. And then what did you say, Jason? Yeah, a couple people earlier said, oh, no, you decide whether 8 or 10 goes up here. No, you don't do that, right? You take, because we want the 40, we want this position to be empty in the end, we say, OK, put the 43 there, and then do what with it? Bubble it down. That one gets removed, which is kind of what has to happen here, and you bubble the 43 down. You say, which of the children of 43 is the least one in this case? Swap, if there is a least one, right? So 43 and 8, 8 and 43, and then 43 versus 13 and 14. It goes 13 and 43, and you're done. Okay, that was the remove min. Not too bad, right? Okay, let's go back to what we had. Let's see, go back to what we had, which was 43 and 13 and 8 and 5. Okay, if I want to add 6 to the heap, how do I add an element to the heap? Jason already answered. Somebody else. Jason's the only one. Allison or Ellie.
Add it to the next spot, which would be the left child of the left.
Good. Add it to the next open spot, so we add a 6 there. And then what?
And then compare it to its
Right, we
leader.
bubble it up, right?
Father.
Compared to its father. Parent, maybe? All right. So you say, OK, look, is 6 bigger than 11? It is not, so we swap them. 6 and 11, and then what?
6 bigger than 10.
Keep going, yep. 6 and 10, and then what?
6 bigger than 10.
6 bigger than 5, and we're not, and we're done. Right? So we've added an element to the heap, and it's relatively straightforward. This is log time. Pretty good. Pretty straightforward and pretty easy to do, and actually not that hard to code either. Okay? I know Ethan's done a whole bunch of heaps and knows this is not that hard to code, right? We all practice this. So yes, that's that. Describe the procedure to add a new element. Well, that's kind of what we just did. That's exactly what Allie just did. I would probably ask you to do it. What I'll try to do is not just give you an empty thing and say fill it in, or an empty box. Like maybe I'll give you a couple boxes and say do each step along the way or something like that, so I can tell the algorithm you used. I mean, I guess that's the idea. Or maybe I'll just say tell me the algorithm, then do it. We'll see. Okay? Questions on heaps? That was the first big thing. Next thing we talked about after that was sorting. Now, you guys have all done lots of sorting over the last few weeks, or a few weeks ago for that homework 4. We covered a whole bunch of different sorts in here, right? We covered insertion, selection, heap, shell, merge, quick, and radix. Whew, it's a lot of sorts. You should know the algorithms for all of those. Does it mean you should be able to like program them all? No. You had to do that for your homework assignment. But I should be able to ask you, hey, what's the quick sort algorithm? You say, oh, look, you take a pivot, right? And you make all the elements that are lower than the pivot, put them on one side, and all the elements that are bigger than the pivot on the other side. Like the details are the part that takes time to program. But you should be able to tell me the basic algorithm, right? Let's see. You should also be able to describe the asymptotic complexity. I'm not talking about deriving it, but I'm saying, I might say, which is what I asked a lot of you guys during the in-person grading for those that I graded. Look, what about selection sort? Is there a way you can make selection sort order n for any type of input, right? And you all went, no. Some of you guys went, sure. No. And then you figured it out. But all you figured it out, right? But no, you can't, because it always has to go through every single one. So you should be able to talk about that, right? You should be able to talk about, hey, what is it about merge sort that makes it log behavior, right? Well, it's the same with quicksort. You're breaking it in pieces, right? Divide and conquer. Big idea. Yes, Sally?
We still get a one-page.
You still get a one-page cheat sheet. Yep, back and front, handwritten, back and front. What else? Handwritten, back and front. I think that's it. Yep. You can bring a calculator, too, if you really want to. Maybe you have to do maybe if you do modding for the hash tables or something, you might need a calculator. Yeah. Oh, if you haven't picked them up, I've got the box of cheat sheets from last time. But if you want them, should I give you 2 pages? I think the last one and this one, I don't really care. I mean, it doesn't really matter to me. I think you'll be fine otherwise. But yeah, if you haven't picked it up, you can come to my office and sort through them all. I haven't sorted them. Sort through them, yeah. No pun intended. Look through them. Find yours. Search through them. All right. OK. So what else are some of the key things about sorting? Well, first of all, most of the sorts we've talked about are these comparison sorts. You compare two values, right? The obvious one that we didn't talk about, or that we talked about that isn't a comparison sort is a radix sort, right? You're actually doing like calculations based on the actual the tens place for a decimal radix sort, and that is not a comparison sort. So comparing a radix sort to a comparison sort is a little tricky, but you still should be able to talk about the complexity in general. As I said, divide and conquer, that's how you get to log behavior. N log n is the best a comparison sort can do, right? Comparison sorts provably, we haven't proved it in here, but if you take algorithms class, maybe you will. Provably is the best you can do for a comparison sort. Okay? Other sorts like radix sort, you can do, quote, better, but again, comparing those two is difficult to do. You can do sorting in place. Sorting in place is great because you don't use extra memory, maybe one or two extra little spots, but not extra memory. The tricky part about in-place sorting is you have to make sure you don't overwrite things, right? You kind of have to make your algorithm take that into consideration. And then finally, I asked a lot of you guys about this too. There's some overhead associated with various sorts. Quicksort in particular. You're not going to use quicksort for a 10-element array, right? It just does not make any sense, because you've got to do all the partitioning and then call recursive calls. And by the time you've done all that, you could have been done with it with an insertion sort, right? So there's no point in doing that. And that's why most sorting algorithms that use quicksort have a little, if I'm less than 10 elements, just do a different type of sort. Like it's built into the code that way. Okay. Radix sort has an overhead, right? Like the whole radix, the idea of finding the radix, right? You got to do divides and mods and all that. And that's again why radix sort, even though on paper it seems like it would be faster than, say, quicksort, it's not necessarily going to be, because you still have to do all these other calculations that kind of outweigh those benefits. So you should know all about that. Questions on sorting? Yeah, Margaret.
For my readme for the sort document, and what I believe the Wikipedia page says, it says insertion sort, the best case scenario is like O(n).
Insertion sort is, not selection sort. Maybe I misspoke. Did I misspoke?
What is you said O log n is the best comparison sort?
Oh, sorry. On average, yes. So, well, yeah. Now, on average, yeah, sure. If you could have, you could have. Here's my sort. It's called the nothing sort, right? Go. Is it sorted? Yes, I'm done. Right? Well, that's our constant time, right? But I mean, it's not correct. But I mean, it's like in some sense you can get better. I guess you at the very least have to go through all the elements once, right? So that's O(n), sure. You at least have to do that. But on average, you can't get a comparison sort for random data that's going to be better than O(n) log n. Yeah, I guess I should have said it that way. Yeah, good question. Yeah, Jason.
Can I ask any questions about like what's the best case scenario? Like what situation would cause this to operate?
Yeah, I could ask that, sure. I mean, just like Margaret's saying, I mean, I could say, in what case would, for instance, here's a good question. What is the case where quicksort is a terrible algorithm? And you could say, well, if it's already sorted and you pick your position, or you pick your pivot terribly, then yeah, you can end up peeling off one element at a time, right? Or you could say, what if they were all the same? Right? I mean, if you try to sort when everyone's the same in quicksort, it's just going to take O(n) squared time the way the algorithm is built. So yeah, I could ask those questions, sure. Yeah. Okay, good question. Anything else? Sorts? I think we've hammered sorts pretty good. What are some examples? We kind of went over all these. Demonstrate how to merge two already sorted arrays. If you did merge sort and for one of your sorts and you came to see me, I asked you exactly this. I said, hey, how do you merge these two already sorted arrays together? And it's very simple, right? But you should know how to do that. I may ask you to perform a few iterations of a particular sort. Like after 4 iterations, what's this array look like? And I would probably not just say it like that, because that would be, but I'd say do the first 4 iterations and see how you do on that. Probably not quicksort, but you never know. I could. Right? Okay. Good. All right. Then we went on to hash tables, and I know you guys have gotten some of you guys have gotten a lot of practice with hash tables over the last couple weeks. It is a little tricky, but once you get the idea, you go, oh, I get it. right? Hashing, remember, produces a number. You take a something, whether it's another number or a string or something, apply some mathematical function to it, and you get a number, right? And that number is what you use to index into an array. And that's what makes it so fast. Once you have that index, you know I can go right to that memory location and get the data there. Okay? The lookup is the exact opposite, right? Well, more or less the same procedure. You hash what you're looking for, go to that index and say, hey, are you there? Because it should be, right? Like hopefully it is just right there in that bucket. And if it is, that's constant time. Yay. That's why hash tables are awesome, right? Because they can get constant time lookup and insertion. So it's great. Well, you can't always get constant time lookup. How do you end up not getting constant time lookup? Collisions, right? And collisions are kind of the bane of the hash table. Like the perfect hash table, its one little wart is the fact that it's got collisions, right? You're never going to get rid of collisions. Okay? Even for very good hash functions, for 2,000 different hashed values out of a 1,000,000 bucket array, you can still get a 95% chance of one collision. Right? It's the birthday problem all over again. Okay? And so that leads to the idea of how do you handle collisions? Because you have to. Right? Well, we talked all about chaining, right? Chaining's a fairly straightforward method. You just say everybody whose bucket is, everybody who's supposed to be in this bucket, get in a line. Right? That's all you do. You're supposed to be in this bucket, okay, get in line. And that's how you do chaining. Chaining is nice because you don't need to find a new bucket. You found it instantly, right, the whole hash. And you don't have to expand. Now, some people were asking me, are you sure we have to expand the hash table if we do chaining for this song search? Well, let's say you picked a nice 1,000-element array for your song search hash table, and you decided to do chaining, right? And there's 30 million unique words or something, or whatever it is, right? Or something like that. Well, all of a sudden you're going to get 10,000, and then you're going to have these giant long lists you have to look through. That's ugly, and it takes time, and it takes a lot of time. Okay? Not so fun to look through linked lists. Or you can make it into a vector or a sorted vector or whatever, but that all takes more time. Okay? So that's the downsides to that. It also adds a different structure to the table, right? So you've got this other structure you have to deal with. Not only is it just a hash table, it's also linked lists or some other vector. So not too fun. All right, what other types of chaining or hash collision strategies do we have? Well, we've got open addressing, right? You've got this idea that, okay, if my hash tells me to go in this bucket and the bucket's full, well, I'm going to go somewhere else and check a different bucket. Okay, and that's what the probing is doing. Okay, you've got a linear probe, which is the easy one. Hey, this is the bucket I'm supposed to go into. Oh, you're full? Let me check the next one. Oh, you're full? Let me check the next one. Oh, you're empty? I'm going here. Easy, right? It's the easiest thing. It's a very simple strategy, right? The problem is when there's groups of hashes that all kind of go to a same location, well, then you end up with these big, long probes. You have to keep probing, and that kind of degrades into the same linked list type of behavior. Not so great, although this works fine. And the way I implemented one of my song search programs that I wrote for this thing, I used linear probing, and I showed you guys how to do that on Piazza, and it works fine. It's not the fastest thing in the world, but it works fine. Yeah.
So you were mentioning that we had the option to make our own hash functions.
Yeah.
You didn't recommend it because it takes a lot of expertise to make
Yeah.
a good hash function.
Yes.
When you talk about making a good one, is it one that makes it so you don't end up with these groups of hashes?
Yeah, a good hash function does a few things. It tries to spread out the values as much as possible, right? Which is good because then you don't get as many collisions, number one. Number two, it tries to not have them in groups like that. I mean, not just colliding, but also not in groups like that. It also needs to be fast. And so it's kind of a combination of all those things. But yeah, and if you want to write your own, that's cool too. But I think this time was probably better to just take this one. Yeah. Okay, so that's the simple one. Well, what's the next level up in terms of these probes? Well, you can do a quadratic probe, right? You could say, hey, when a collision is detected, don't step by just one. Go farther away and check that. What's farther? Well, x plus 1, x plus 1, x plus 4, x plus 9, x plus 16. In other words, quadratic, right? And you still have to wrap around the table when you get there. This is better because you're generally not going to have to worry as much about groupings like hash groupings. You are, however, going to have to be a little careful that you have your table set up so that you don't skip groups and like end up in some loop where you end up skipping and there's free spots, but you never see them because of your strategy here. Okay, that's not so great. Okay, and if you get too big on this, well, then you end up kind of looping all the way around your table, right? That wouldn't be so great, but you could, it would work. Yeah.
When I was experimenting with collisions, I tried both this and linear probing,
Mm-hmm.
and I found that I got the exact same number of collisions with both of them.
You will get the same number of like initial collisions. Oh, not necessarily. Oh yeah, not necessarily.
They found a bucket that's like already on.
Oh, they found a bucket the same amount of times?
Yeah.
Interesting.
So I was wondering, like, if that's the case, is there really a benefit to using this as opposed to linear probing?
There's probably no benefit to using this, and this may go back to what Dylan was saying. And the guy who invented the hash function, probably made it such that it's very well spread out. So it might not have mattered so much. Yeah, but it's another idea, especially if you do have hashes that do group up like that. Okay, well, what's another one we can do? Well, we can also do double hashing. The nice thing about double hashing, and double hashing is where you hash it. If it goes into a bucket that's already full, you take a completely independent hash function, rehash the key, and then it will go to another location. Right? And then you can add some other things to do some other kind of probing. But once you do that, you then say, let's say two things go into the same bucket, and one goes to another location. Well, the next thing that goes into that bucket will not also go to that second location. It'll go to some other location because the hash function is completely different again. So it really spreads things out. Okay, not a bad idea to do this. Lots of hash tables do use double hashing because it spreads things out pretty well. Okay. Again, you have to be careful about expanding these. Yeah, Jason.
Wait, so you're saying, so like if the first thing hashes in this bucket that's already full, and you have two things which are exactly the same.
Yeah.
And you're going to apply the first hash function again. They're both going to apply to the thing that's already in that bucket. But then the second time, you apply a different hash function for both of them?
Yeah, well, watch. So let's say I have a number and it hashes to here, and that one goes there. So that one's now that one's full. The next one comes in, it also goes there. I apply this other new hash function, it says, no, go here. Right? Okay, I have another number come in, and it says, go here. And then I go, oh, I'm going to rehash it. It's not going to rehash to this bucket. It's going to rehash to some other bucket. And so it's not going to jump to this one. It's going, because it's a completely independent hash function, it's going to say, oh, I want to go here. Right? Two different hash functions that they're doing that. So that's where you get the mix and match in that sense. Okay? Question is, what happens when you have the double hash, both hash, like have a double hash collision? Well, then you got to deal with that too. It's a little more complex.
When you have a double hash collision, you just probe on.
You can just probe, yeah. I mean, it's a little more complex, but otherwise you can do it. Yeah.
How do you keep track of which secondary function is used for which?
You just have two functions. You always use the first one, and then you always go to the second one. And then, like Jason said, if that fails too, then you have to do some other probing strategy as well.
But it would probe by whatever jump the second hash is.
Right. Like you could include the jump try into your second hash function or whatever. Yeah. Yeah.
Would you go back to the original hash function, but append your hash values to the string that you initially hashed?
Could you go back? You could. There are probably lots of different ways to do it. Yes. You could probably go back and have something. That would be harder to do than you think, believe it or not, because those kinds of like appending things tend to degrade rather quickly. But yeah, but you could do that. Sure. Why not? Yeah. Good. Okay. So that's collisions. Remember, if you have open addressing, at some point or another, if you keep adding elements, you will have to increase the table size. Not true for chaining, but you probably want to anyway. And in open addressing, you definitely have to, so you'd better know what the load factor is. The load factor, simple as this. Number of elements that are already in the table divided by the table size. That fraction is what you should compare against to determine whether or not you want to expand. What's the comparison? Well, it's empirical. You should probably leave it relatively small. Less than 0.7 is good. Less than 0.5 is really good. Problem is, if you have it at 0.5, then you will always be wasting half of your table elements, because every time you get to 0.5 or bigger, you will double the table size. Well, that's okay in some sense, because you want speed, right? some people are asking good questions about, oh, once I get done with my inserting all the songs, can I go back and reduce that table size down to what I want? Sure, if you want to do that. We're not going to add any more songs, so you can do that. It's just another idea for saving a little bit more memory. Okay? But the point is, you've got to expand for this type of system, and you're going to want to expand for chaining many times too. How do you expand? Well, this is the tricky part, right? I've seen a lot of people with errors in their expansion things for this project. When the load factor gets big enough that you're going to have to expand, create a new table, and then instead of just copying values in, rehash all the values to their new location in the new hash table. Okay? Is it slower than copying? Yeah, it's not the fastest process in the world. But it's faster than, it's necessary because first of all, you could run out of space in your table and then you'd be done. But second of all, it's probably in the end going to outweigh the idea of leaving your load factor really high. Okay? It's a little bit of a trade-off, but you have to rehash. If you didn't rehash, you would lose that, the hash values that you copied in would not be in the right place. The values would not be in the right place for the previous hash because you're modding against a different table size. That's the big thing. Okay? Questions on expanding the table? No? Those of you who have done it have gotten through the pain of it, but it's I put the algorithm on Piazza if you're still confused about it. Okay? All right. So hashing is not just for hash tables, right? There's also cryptographic hashing, which we talked about. Cryptographic hashing is where you have a one-way function. At least you hope it's one way. In other words, you hash some key into a value that it's hard to go back to the key again. Why is that good? Passwords, right? Digital security in general depends on this idea that you can go one way to get a hash, but you can't go backwards very easily. Okay? And it's not just that you can't go backwards. You can't go backwards to find any key that matches that hash function or that hash value. Okay? Passwords, digital signatures, all these things are very highly used with cryptographic hashing. You should know about the 4 different properties of cryptographic hashing. Okay? It's easy to compute the hash value. That does not necessarily mean fast, but easy in the sense of it's not particularly taxing to do the hash value in general. Because especially for if you're going to encrypt a lot of things and you want to be doing these hash values often, you don't want to have it take a lot of processing power. Sometimes you do, right? With passwords, you want that to be a slow process so that brute forcing it is slower. You don't want to be able to generate a message that has a given hash. Like I have the hash, hey, what's the message that made that hash? You don't want that because that would make it easy to break it. You want it to be infeasible to modify a message without changing the hash, right? So this was the idea that you had 2 passwords that were very similar, hello and HELL 0 or something, right? 2 passwords that are very similar. You want those to create completely different hashes. Why? Because I don't want Margaret's hash and her password to give me to show me that my password's close to hers because of the hash value being close to my hash value. You want them to be completely separate. Okay? And of course, you want it to be infeasible to find 2 messages with the same hash. You want the collisions to be as low as possible. Okay? It's not going to be 0, but you want it to be as low as possible. Okay? All right, so that's cryptographic hashing. Here's some questions I could ask about hashing. I could say, let's say we have the hash function is x mod 9, and the table size is 9. Hash the following keys, 5, 29, 20, 0, 27, and 18. Okay, and the first one we're going to use chaining, and the second one we're going to use linear probing. You want to actually do that? Let's do it. Why not? All right. So here we go. It's going to be a table size of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 0, 1, 2, 3, 4, 5, 6, 7, 8. OK. So we're going to take these numbers. It's going to be the hash function is going to be very simple. Right? Hash, it's going to be the key mod 9. OK, so 5. 5 mod 9 is what? 5, right? So 9 is going to go right, or sorry, 5 is going to go right there. OK, what is 29 mod 9? 2 actually, right? 27, 3 times 27, 2 remainder, right? So 29. Is it? I'm right, right? Yeah. All right. 20. Also 2, because 18 goes in with 2 remainder. Well, now what you do is you say, oh, OK, we're chaining now, right? 20. OK. And then 0 is 0. 27, 0. Or it's the remainder, right? Right? So 27. And then finally, 18, also a remainder of 0. Right? 18, a remainder of 0. So this is what your table looks like after you've put everything in there, right? How do we search for 18 in a hash table? Lydia? Good. 18 hashes to 0. Is this 18? No. Is this 18? No. Is this 18? Yes, there it is. Right? And we're generally not going to store just the keys in there. We're also going to store some other stuff like a song or something like that, right? Or a vector of songs with frequencies or whatever, right? So that's how you do that. OK, so that was the chaining. Not too bad. Let's go back and do it with linear probing. Okay? All right. So if we put 5 in there, 5 still hashes to 5. So 5 is going to go right here. All right. 29 still hashes to 2. So 29 is going to go here. 20 also hashes to 2. OK, we go here and we go, nope, can't go here. We better go 1 over. Yep, it's empty. We can put 20 there. OK. 0 hashes to 0. Right? And that's empty, so we can put it there. 27 hashes to 0. Oops, we're full. Better go here. Right? And then 18 hashes to 0. 18, oop, busy. Full, 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 full. 18 goes there. See how that works? OK, our load factor is 1, 2, 3, 4, 5, 6 divided by 9. 0.67, it's getting there. Probably should start to think about expanding. How do you search for 18 now? Hash it. 18 hashes to 0. Right? Is it 18? Nope. Is it 18? Nope. Is it 18? Nope. Is it 18? Nope. Is it 18? Yep, there it is. Right? Okay. If we tried to hash something that wasn't in there, right? Let's say we tried to hash 6. Well, 6 hashes to 6. Well, you got, yeah, right there. OK. How about, let's see, what else hashes to 30? Which hashes? 36 hashes to 0. So 36, boom, 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 boom. You stop when you get to a null value or some sentinel that tells you what the value, that there's nothing there. OK. Good. All right. Let's see. Oh, let's go to 3 for a sec. Explain how an element should be deleted. So let's say I delete 27 from this hash table. Right? Can I just delete it? I can't just delete it. Because then when I look for 18, I go, is it 18? Nope. Is it 18? Oh, it's empty. I'm done. Nope, but 18 is in there. Right? So you need to somehow mark it as, you're deleted. You can put something there next time, but you just have to mark it for being deleted. Okay? Or do some fancy moving, but you might as well just mark it for now. All right, write the insert function for a hash table that uses quadratic probing with a quadratic probe jump of x squared. It's actually, I guess the jump would be x, and then the jump, I guess the attempt would be x. And so you do x squared to do that. So write a little function for that. It's not too bad. OK. Questions on hash tables, types of questions I could ask. OK. All right, then we talked about graphs. Graphs are super duper important. I know we did this at the end, right? But graphs are super duper important. You will see these again when you talk about algorithms, when you talk about other types of classes, CS classes in kind of more theory. You'll get into lots of graph stuff. Okay? Graphs are similar to trees, except there's no structure. It's like the Wild West, right? No structure here, right? You've got vertices pointing to anybody, and any vertex can point to any vertex can point to any other vertex via an edge, through the graph, around the graph, whatever. It doesn't matter, right? Which leads to other behaviors, which are kind of interesting. And graphs come up all the time in real life. There's not as much structure as we always might hope for in real life situations like this. Okay? We can talk about undirected graphs, right? No arrows. Or we can talk about directed graphs with arrows on them, saying 3 can get to 10, but 10 can't get directly back to 3. Okay? In fact, 10 can't get 3 at all in this case. You can talk about graphs with weights or not. Weights being the number that tells you what the weight is to get from one vertex to the next. Okay? Those become really important when we talk about shortest path algorithms, which are kind of the key one we talked about. Okay? Two that we're going to talk about that we mentioned. One was an unweighted graph. The more general case is the weighted graph, which really is just it's a general case. The unweighted is a special case of the weighted where all the weights are 1. Right? So we're going to talk, we have to kind of refresh our memory on some of those. For the unweighted one, I'll give you the algorithm here. Pick the starting vertex. Okay? You know that to get to itself, it takes 0 weight, like there's 0 cost or 0 path. Then you take that vertex and you say, what is adjacent to me? And then you add 1 to your current path length, and then you go to those ones, and you go to those elements, and you say, who can I get to? And if you get to one that points back to one that's already got a weight, you can ignore it because that weight is already going to be less than the one you might calculate by adding 1. Okay? And you keep doing that until you have until all the nodes have minimum distances, or all the vertices have minimum distances, and you're done. Okay? Here's an example. Okay? You take a look at 0, and then 0 goes to 1, and 1 goes to 2. Goes to 2 and 4, and it's just adding 1, and then adding 1 more, and then adding 1 more, and then 2. When you get to 2, 2 goes to 4, but you're not going to add another. It's not going to be 1 plus 2 plus 1, 3, because 4 already has a length of, or a path of 2. So you're not going to update that one. Right? Same thing with 6. You're not going to say, oh, going from 1 to 4 is 2. Well, from here to, 0 to 1 to 4 is 2. And then adding another to get to 3 here, you're not going to do that because it's already got a path length of 1 from 3. Okay? All right? And I think that's it. Yeah, we actually finished them all up this way. Oops. Questions on the unweighted algorithm? It's pretty simple. Okay, then we finally get into, let's see. We finally get into Dijkstra's algorithm here. Dijkstra's algorithm, this is the famous path finding algorithm, right? And the idea of Dijkstra's algorithm is be greedy. Do the best thing you can at the time you get to a certain position. Might as well, right? It seems like the best thing. It turns out that it's a greedy algorithm that works, which is great. Okay? So we have these tables here that say, OK, here's all our vertices. Here's whether we have known them or not. And this is the distance. And remember, the distance to everybody is unknown except for the start. Like the start knows that it's 0 to itself. Everybody else, it's infinity right now. As far as we know, it's infinity. Okay? And then you also have this previous column here which says, hey, how did I get to you? Right? It wouldn't be so good if you had Google Maps, by the way, which uses a slightly modified algorithm like this to get you where you need to go. If Google Maps said, if you said, I need to go to Chicago, and Google Maps said, OK, the fastest path to Chicago is 722 miles. And then that was all it gave you. Right? I mean, you wouldn't be too happy about that. You'd be like, well, thanks, Google. You're not helping me much here. Where do I go? Right? You've got to be able to find the path, not just know the shortest path. You have to be able to find it. So that's what we want to be able to do. All right, how do we do this? Well, look, we start out and we say, OK, it was 0 to the start. And then what is adjacent to the start? 2 and 4. So OK, so I'm going to update. I'm going to take vertex 1's distance, which is 0, plus 2 to get to 2, and then make vertex 2 equal to 2, and vertex 4 equal to 1. And so I do that, 2 and 1. Everybody else is still infinity. And the only thing we know right now is 1. And then I start over and I say, OK, well, of the remaining ones that we don't know, who's the least? 4 is. So I go to 4 and I go, who can you see? Oh, I can see 3 and 6 and 7 and 5. And I'm going to update all of those. And it does. It updates all of them, which is here. Right? And then everybody has a distance, but they're not necessarily the minimum yet, because we still have all these unknowns. Which one's the next unknown? Oh, it's 2. Then it's 2, and then we go to 2, and we say, OK, 2 can go to 4, but that's already completed. It's already less. We don't worry about that. 5 is also less, so 2 doesn't have to do it, etc. Okay, do you remember how this one works? It's all on the slides. Okay, and you keep doing that. Yeah, Allie.
Does it really matter if you pick the shortest path first? Like, you start at the first vertex and then a vertex.
Yep.
And then you see 2 and 4, and 4 is closer. Does it matter that you look at all of 4's nodes?
It does matter. It wouldn't. Well, first of all, it wouldn't be greedy if you weren't doing it that way. But yeah, it would matter because then you'd say that look, 2 is complete after you go to 2, right? And if you complete it, and then let's say there was a path this way that was actually shorter, you would never have gotten that shorter one.
Right. 'Cause
Right.
The path
Yeah.
to 2 could be like
Yeah.
40.
So you want to always pick the remaining ones that are not known yet, and then it's the smallest of the remaining ones. For ties, it doesn't matter. Like in this case, once we did 2, 3 and 5 tie at 3. It doesn't matter. But if there is a smaller one, you have to go that way. Yeah, Dylan.
Do we need to worry about hitting dead ends?
Okay, so if you hit dead ends, it doesn't really matter because you're still going to just go back to the adjacency table and say, hey, which one are still unknown? You're always going to go until you get all of them known. So it won't matter. Now, there may be some unreachable nodes. That's fine. They'll end up with infinity still. If they're unreachable, the way to get there is infinity. It used to be on Google Maps. You might still be able to do this. If you type like New York City to Hawaii, it'll take you all the way, drive you all the way to California, and then say canoe to Hawaii, right? And then then it says in Hawaii, it gives the rest of your directions. But I mean, the point is Hawaii is not reachable by car anyway, right? So it should be infinity. But Google kind of cheated a little in that sense. Okay. I don't know if you say to go to the moon, it might say take a rocket or something. All right. So anyway, these are all from the previous slides, but basically you just keep picking the smallest of the ones that are not remaining, and you do it. And then to go find the path, which is important, right? If you say the least path to get, or the shortest path to get to 5 is the shortest path to get to 5 is 3. How did we get there? Well, we came from 4, so let's go back to 4, and then from 4 we came to 1, and then we're there. Right? So that's how you just go backwards and reverse the path backwards. Okay? This is, like I said, this is how Google Maps does it. Google Maps doesn't necessarily get it right all the time because they can't necessarily predict all the weights properly. Right? Distance-wise, they're fine, but in terms of traffic and in terms of time, it's much harder to predict. Okay? But there are smart people working on it, and I guarantee you those people know Dijkstra's algorithm and know about graphs. People are working on that. Okay, what kinds of questions could I ask? Complete the adjacency matrix or adjacency list. You should have done this in lab one day where you said, hey, what's the adjacency matrix for this graph? Not too hard to figure out. You should also be able to state the breadth first or depth first traversal. Breadth first, you go to a node and then you go to its immediate adjacent ones and handle those ones. Then you go to their immediate adjacent ones. Depth first says start at a node, go down to an adjacent one, go from it to an adjacent one, go from it to an adjacent one, go from it to it until it stops, then backtrack your way up, and then go down the other path. Those are the differences there. Okay? To do a breadth first, you're still going to need a queue of sorts. Okay? Shortest path unweighted and Dijkstra's. Should be able to do both of those. Yeah, Margaret.
In lecture you talked about what happens if paths are negatively weighted.
Oh yeah, I didn't cover that in the review. You should probably know about negative weighted ones, but I'm not going to ask you to try to redo the algorithm for Dijkstra's with negative paths or anything like that.
You should know they exist.
You should know they exist. You should know why it's harder to deal with them. Circles are bad, because you keep going around forever and keep getting less and less and less. Yeah, good. Okay, so I believe, yep, that was the end of our review for the test. Any questions on the review part? No? Okay, so I just wanted to spend a couple minutes talking about what we talked about on day 1, which you might not remember now, and I actually told you don't need to remember it. I wanted you to get like kind of the general feel for some of the stuff we're going to talk about. But here's what I did on day 1. I mentioned 4 different containers, right? And I said, there's a container called a dynamic array, which you should know about already, and then a linked list, which maybe you've heard about, and you had. Most of you had heard about this. And then I said, and you should probably heard about, and then you need to know, and then I'm going to use this thing called a hash table, which you haven't heard about yet, probably. And most of you are like, no, I have no idea what that is. And then a binary search tree, and you're like, no, I have no idea. Well, now you do know about these things, right? And you do know about some of the actual results that we can get with this. But here's what I showed you, okay? I said we're going to take these 4 containers, and we're going to do the following. We're going to add 100,000 elements to each container. In particular, we're going to add the even numbers from 0 to 200,000. And then we're going to search for 50,000 elements. We're going to search for 0 to 50,000, including the odd numbers, which means that half the searches are going to come out to be not true, like not in the container. And then we're going to delete 20,000 elements. We're going to delete the elements, the integers from 1 to 20,000. Okay? And that's what we decided that I was going to do. Here are the results I showed you on day 1. Okay? Now, I said, all right, look, here's this thing called an array, and it does pretty good. Right? Inserts are really fast. Search is not so great, but OK. Deletes, not so great. Linked list, horrible. Right? Right? And then inserts for linked list are great. They're pretty fast. Searches, terrible. Deletes, kind of terrible. Right? Why? Because and you guys know all this now, right? It takes time to search through a linked list because you have to go in order. And it's slow to go in order because it's a node-based thing, and it's just not a fast type of thing, right? Inserts, sure. In fact, if we had redone this where we're inserting in the middle of things, arrays might have beat out vectors, but that's about it. All right, then we go to hash tables, and we go, wow, look at this, right? Fantastic time here. Great inserts, great searches, great deletes. Now you know why, right? Hash tables are all constant time behavior for all these things. Okay? Binary search trees, same thing, pretty good across the board. Not quite as good as hash tables, but pretty good. And then I threw in this sorted array, and I said, if I know it's sorted, even though they're all sorted, I said, if I know it's sorted, I can apply a binary search on it. And look, searches go way, way down, right, compared to the up here. Why? Because it's a binary, it's a logarithmic function, right? And so hopefully at this point in the class, you've gone from, we started on day 1 when I put this up there, and you went, oh, too many numbers. And then now you're like, oh, yeah, I get why this is the case, right? You can kind of go through all this and go, oh, this is really why these work the way they do. So then what I did was this morning I said, oh, how about I just try 1,000,000 of all these? Right? And here's what happened. All right? So arrays, 163 seconds. Inserts still really fast. Search is terrible. Delete's kind of terrible. Linked lists. Let me put it this way. My fans totally came on the computer. They were like, whoosh, right? Because this was just like, oh, right? I mean, that's 1,000 seconds, like 15 minutes, right? Just sitting there, if you're 20 minutes, just sitting there like, da-da-da, I'm doing this thing, right? And I just sat there and did it for 1,000,000 stuff, right? Why? Because searches took forever. I had to go through 1,000,000 things every time for 20 or 50,000 things or whatever, right? It was just a pain, right? And delete, same thing. It just takes a while. You got to search for it, then delete it. Hash tables, amazing, all right? Right? I mean, still like 0.12 seconds. I mean, you're not going to use a hash table you're not going to use a linked list for searching. Forget it. Binary search tree, also pretty good. Pretty darn good. Sorted array, not great. Really, the hard part is deleting, right? Because you have to find it, then delete it. And deleting in an array, as you all know now, you have to move all the values. What a pain, right? Even if it's a sorted array, you still have to move all the values to do that. But that's that. Now, let me just compare them directly here. All right, well, look at this. Arrays went from 1.67 to 163 seconds. It's an order of 100 times. Now, keep in mind, what we're not talking about is n squared here. We're actually talking about linear behavior, but you're doing 10 times as much work, right? So 10 times as much work, right, means you're going to have, and if it's linear in that case, you're going to have 10 times as much work to do, but it's going to take 100 times much more time. Okay? Sorry? Well, it's kind of, well, okay, I guess it is n squared in the sense that you've got, each element is going to be take a linear amount of time. So you're doing 10 times more stuff, and you've got 10 times more stuff to look through. So it's going to be linear times, like 10 times 10 in that sense. So I mean, I guess in some sense it's n squared, but it's not really comparable to our sorts, like in that sort of behavior, right? Linked list, roughly 100 times difference, right? Even more. Hash tables, 10 times different. 10 times as much stuff, 10 times as much time. Awesome, right? Why? Because you're just doing 10 times as much stuff and it's constant lookup. Great. Binary search tree, about the same. This should be about 30 times difference. It's a little less. I'm not sure if they're doing some fancy down under the covers in this one, but it's slower, but not too bad, right? It's not a factor of like squared type factor. And sorted arrays, not so good here because basically you still have to do all that searching. Okay, good. All right, and then we have the inserts. Same difference. It's all the same ideas here. Inserts, and then the searches, right? Searches were all sorry. For the sorted array, you had to do all the deletes still, but the searches are still great for sorted arrays. Yeah, question, Lydia.
Did the hash table in this example rehash?
I'm not sure if the hash table rehashed. To tell you the truth, I'm not sure. Probably did. Probably did a number of times, yeah. But in the end, it amortized the behavior. Okay. All right. So I just wanted to bring you back a little bit. Now you guys know all this stuff. What didn't we cover this semester? Well, there's about a million different data structures we didn't cover. Why? Well, because we only had a certain amount of time. And what we did cover was the basics of we covered the base models for all these algorithms, right? If you want a tree, there's also B trees, there's KD trees, there's radix trees, there's occ trees. I don't even know what that is, right? Right? If you want hash tables, there's height maps, which is kind of a table. There's a rolling hash, right? If you want lists, there's a skip list or a difference list. All these things, multi-graphs, right? I have no idea what a spaghetti stack is, right? But the point is that now, since you've been through this class, you've gotten to a point where you've said, OK, I know the base models. If I'm going to go to Google and write some new algorithm for them, right, I know I'm not going to use a linked list for their searches, right? I'm going to use some form of hashing, right? Or at the very least, some form of tree behavior or something. And maybe I'll find something that works a little better because lots of people do research on this stuff. But I'll know the basic idea of a tree. Okay? As far as interviewing goes, you guys are very prepared right now to go and interview a lot of tech companies, right? They would ask you lots of questions about data structures. Why? Because they want to know if you know these base model things. Now, they might throw a zinger at you and say, hey, there's this thing called a 2-3 heap, right? I want you to do something. And you go, I haven't heard of that. They go, well, you know what a heap is, right? You go, yeah, I know what a heap is. And you tell them what a heap is. And they go, well, this is what a 2-3 heap is. And then you kind of think, you go, OK, I can get it. I know somebody who, Ashley, who was one of the TAs, she had an interview where they asked her about a trie. And she had not seen tries before in data structures. Her class didn't do tries. But otherwise, you can, but you know the basics now, right? And the idea is you want to use the best data structure for your task. Whether or not it's a base model or it's something special, at least you know how to start the analysis for it. You know how to analyze it asymptotically. You know how to, you know what's going on kind of under the covers, which is the whole point. Okay? Questions on that? Just want to throw up some of the things you can still look into. Okay? All right. And then finally, there's some references here. I put a bunch of references on. The visualization one's a great one. More stuff on the list of data structures. It's huge. And some other programming things. So we have arrived, the last day of class. And I wanted to say I appreciate you guys bearing with my mistakes over the semester. This is my first time at Tufts, so I didn't know exactly what to do in a lot of cases, but you guys were very patient in most cases, and I appreciate that. I know you're working hard on this final assignment. Again, please don't stress about it. You'll do fine. Do the best you can, and you guys are great. I've enjoyed working with you, so thanks. Oh, thanks. Any last minute questions? No? All right. We'll see you guys in lab today or on the final.